Welcome to our explainer on the greatest discoveries in modern cosmology. Today, we are going to carefully untangle the monumental breakthroughs in radio and microwave astronomy. These are the specific discoveries that completely redefined our place in the universe. Before we begin our analysis, please take a brief moment to subscribe to the channel, like this explainer, and click on the notification bell so you never miss our deep dives into astronomical science. We have a substantial amount of material to cover today, and we'll proceed methodically to map out the unseen cosmos. Here is our highly structured roadmap for today. We will start with the invisible radio universe. Then, we will outline the 5 pillars of radio astronomy. Next, we will explore the echoes of the Big Bang, followed by unveiling Sagittarius A star. Finally, we will conclude with mapping cosmic anisotropies. Let us begin.
Part 1. The Invisible Radio Universe, Exploring Beyond the Optical.
For centuries, our entire view of astronomy was restricted to the optical spectrum. We could only study what we could physically see. However, the radio band presents an entirely parallel universe. Because radio waves easily penetrate interstellar dust clouds, they reveal phenomena completely obscure to traditional stargazing. This expansion often yielded highly serendipitous results. For example, in 1967, graduate student Jocelyn Bell noticed a strange, repeating signal pulsing exactly 30 times a second. She jokingly designated it LGM1 for Little Green Men. The realization of what she had actually found, a pulsar, the spinning remnant of a collapsed neutron star, was a profound shift in astrophysics. To understand this shift, consider this image. When we look at the night sky above Green Bank, West Virginia, with our naked eyes, we merely see empty space and a scattering of stars. But if you possessed a radio eye measuring 300 feet in diameter, this complex, luminous web of thermal and non-thermal radiation is exactly what you would detect. Radio astronomy allows us to map a universe that was previously entirely invisible.
Part 2. 5 Pillars of Radio Astronomy, Categorizing the Breakthroughs.
As radio astronomy accelerated after World War II, the sheer volume of discoveries created significant overlap in the public consciousness. It is incredibly easy to get these milestones tangled up, so we will establish strict clarity by methodically tracing this timeline. The era begins in 1932 with the detection of cosmic radio noise. We then leap to 1964 for the cosmic microwave background. This is followed by pulsars in 1967, the identification of Sagittarius A star in 1974, and the modern satellite era of mapping cosmic anisotropies starting in 1992.
It is absolutely crucial to tell these apart. We have laid this out in a clear visual chart for you to examine. Notice specifically that Bell Laboratories is responsible for the first 2 discoveries: Carl Jansky's initial 1932 detection of extraterrestrial radio waves, and Penzias and Wilson's 1964 discovery of the cosmic microwave background. These must be entirely separated from the 1974 discovery of the supermassive black hole Sagittarius A star, which was accomplished by Ballack and Brown at the National Radio Astronomy Observatory, or NRAO. Organizing these 5 pillars visually prevents the frequent, critical conflation of these distinct scientific milestones.
Part 3. Echoes of the Big Bang, the Accidental Discovery.
With our categories defined, let us examine the details of the second pillar. What exactly is the cosmic microwave background? Think of it simply as the cooling embers of the universe's fiery birth. Approximately 13.8 billion years ago, the universe was filled with a violently hot plasma. As the fabric of space expanded, those highly energetic waves of radiation were stretched out and diluted. The cosmic microwave background is that residual sea of invisible, low-energy radiation spread nearly evenly across the entire universe.
The historical context of this discovery is fascinating. When Bell Laboratories technicians Robert Wilson and Arno Penzias utilized their horn reflector antenna in New Jersey, they were actually just trying to eliminate a persistent background noise signal. They did not initially interpret their own data cosmologically. It explicitly required consultation with theoretical physicists at Princeton University who correctly identified this annoying static as the leftover thermal trace of the Big Bang itself.
Through their meticulous measurements, scientists determined that the ambient temperature of space is not absolute zero. The once boiling cosmic plasma has expanded and cooled significantly over billions of years. It has now settled at an unimaginably chilly 2.7 degrees Kelvin above absolute zero. That is nearly minus 455 degrees Fahrenheit, which is the true background temperature of our cosmos. The theoretical implications were immense, requiring strict verification. As you can see here, the subsequent data from the COBE satellite perfectly traces the theoretical black body spectrum curve. This highly specific confirmation cemented the Big Bang model. It effectively dismantled the competing steady-state theory of the universe, proving beyond a shadow of a doubt that the cosmos evolved from an extraordinarily hot, compressed initial state.
Part 4. Unveiling Sagittarius A star, the Milky Way's monster.
We will now shift our focus from the expanding edges of the early universe directly to the center of our own galaxy. Sagittarius A star is a staggeringly bright, highly compact radio source situated right at the galactic center. Through decades of extensive observation of the surrounding region, astronomers confirmed that this compact, non-thermal radio object is actually a supermassive black hole.
As we noted earlier, it is remarkably common to confuse the Bell Labs cosmological discovery with the galactic black hole discovery. We want to be exceptionally clear here. The 1964 Bell Laboratories discovery pertains strictly to the cosmic microwave background and the Big Bang. In stark contrast, the 1974 discovery of the Sagittarius A star black hole was executed by researchers using the interferometer of the National Radio Astronomy Observatory. Robert L. Brown later appended the asterisk to the name to denote the incredibly energetic state of this massive object.
To truly comprehend the sheer scale of Sagittarius A star, consider its mass. By meticulously observing the orbit of stars traveling incredibly close to the galactic center, astronomers derived a precise measurement. This supermassive black hole contains a mass equal to 4.297 million of our suns. And remarkably, all of that immense mass is concentrated into a region smaller than the orbit of Mercury. Now, because light is completely incapable of escaping a black hole's gravity, the object itself remains entirely invisible. Yet, by utilizing a global network of radio observatories known as the Event Horizon Telescope, scientists made the invisible visible. In May of 2022, they released the very first direct image of the heated accretion disk. What you are observing is the radio and infrared energy emanating from gas and dust superheated to millions of degrees as it actively falls into the void.
Part 5. Mapping Cosmic Anisotropies, the Satellite Era.
Returning to the vast cosmic scale, we reach our final pillar. Ground-based observations are fundamentally limited by the humidity and interference of Earth's atmosphere. Therefore, mapping the incredibly minuscule temperature fluctuations in the early universe required space-based observation. This ushered in the satellite era, defined primarily by NASA's Cosmic Background Explorer, or COBE, and the subsequent Wilkinson Microwave Anisotropy Probe, known professionally as WMAP.
Over the course of 2 decades, we witnessed a stunning progression in mapping resolution. The COBE satellite provided the initial, somewhat blurry proof of temperature fluctuations in 1992. By 2003, WMAP sharpened that focus, mapping the acoustic peak structure in much finer detail. Finally, the European Space Agency's Planck Space Telescope in 2013 delivered the highly granular map of the early universe that we utilize in cosmology today. The WMAP data was revolutionary because it allowed physicists to extract highly precise mathematical parameters. It established the standard cosmological model, effectively proving that we reside in a nearly perfectly flat universe. Furthermore, by measuring the acoustic waves that rippled through the early universe, the WMA mission accurately determined the Hubble constant, providing exceptional consistency for our models of the cosmos.
Perhaps most significantly, the data derived from these temperature fluctuations provided compelling evidence regarding the actual composition of matter. The precise measurements dictate that only 16.6% of the matter in the early universe was ordinary, baryonic matter. That is the material that makes up stars, planets, and human beings. The remaining 83.4% was firmly established as non-baryonic dark matter.
Cosmology remains a profoundly active discipline. Today, international collaborations continue to probe the microwave background, actively searching for the faint, B-mode polarization. These are the theoretical remnants of gravitational waves stretching across the fabric of space from the era of rapid inflation. As our mapping of these vast, unseen phenomena becomes ever more precise, one must ask, what new, fundamental forces will the invisible radio universe reveal to us next? Thank you for watching this explainer, and we look forward to exploring more of the universe with you soon.